All right, so we're going to continue. We're going to do part 2 of 9-6. But before we get to that, we're going to do it. Well, we'll do a quick recap. This one, number 2 on your warm-up, okay, is a limison. So if we remember, if it doesn't add or subtract, it's a circle. If you have something adding or subtracting, it's a limison. And then once it's a limison, you got to classify which of the 4 kinds it is. Find its max, find its min, use the symmetry to help you plot it. So this one, because it's actually got parentheses, that 3 times 1 minus cosine theta, I would distribute that 3 first. So I end up getting r equals 3 minus 3 cosine theta. Then I know it's a limison because we're adding or subtracting, right? So limison, I know the A is the one that's by itself, which would be the 3. The B is the one that's attached to the trig function, which we ignore the sign, is also 3. And what is true if they are the same? If A over B equals 1?
It's
Cardioid, the heart-shaped one, right? You will. So, like, you'll classify it by what it is, and then depending on what it will usually ask you for symmetry. So the things it will require is what kind is it, and then within the limison specifically, so like of the 4, it's circle, limison, rose, lemniscate. You're going to say this is a limison. And then within the limisons, there's 4 kinds. So you'll say specifically which kind of limison it is. And then if it's a limison, well, with all of them, we're going to add symmetry. So it had cosine in it, which means it's symmetric to the polar axis. So again, all of them, as we get down to the type, you'll then do symmetry. Then with a limison, we specifically do max and min. So our max is 3 plus 3, which is 6. And our min is 3 minus 3, which is 0. Then we want to find where those happen. So I'm going to take my equation, and it doesn't matter if you use the one with the parentheses or the one after we distributed, but we're going to set it equal to the max. So I'm going to say 6 equals 3 minus 3 cosine theta. And the purpose of this is to find out where the big rounded side of my heart-shaped limison is. So then I'm going to subtract the 3. I'd get 3 equals negative 3 cosine theta. Divide by negative 3. Negative 1 equals cosine theta. And where is cosine negative 1? At pi. Good. Remember, unit circle's your friend. If it's not by now, you need to make it. So that tells me that on the side where pi is, which is on the left-hand side of my graph, my max is there, and my max is 6. So I will literally go to the 1, 2, 3, 4, 5, 6th ring, and I'm going to plot my point. It also tells you that the opposite side is where your min is. So if I had continued and set this equal to the min, I would get 0 equals 3 minus 3 cosine theta. Negative 3 would equal negative 3 cosine theta. Cosine theta would equal 1. And theta is 0 because that's where cosine's 1. So it will always be opposite it, which means that on the other side at 0, my point is 0. So I'm at the pole. If you understand the shapes of your limisons, then you know that it rounds on this side, comes in, makes kind of a heart, and comes back out. So then that's an approximation of what it looks like. We're going to actually find one more point to figure out how far out it goes, and then we're going to use our symmetry to duplicate it down to make it more accurate.
How do you know when it pinches in?
Because I know it's a cardioid. When it pinches in?
Yeah, when.
It doesn't really matter as long as you make that sharp little point.
I mean, like, which side?
It's always opposite the max. So we find the max, and then the opposite side is where it's going to make that shape, okay? So I'm going to find how far up it should go, which will then reflect to how low it should go because it's got symmetry, by plugging in a point from this quadrant. So plan ahead. Think about what would be easy to plug in. Of my over 3, over 4, and over 6, what's the easiest cosine to work with? What's easier, a half, root 2 over 2, or root 3 over 2? A half, always going to be easier. So which of those angles in that second quadrant have a cosine that's a half? 2 pi over 3. So I'm going to plug in 2 pi over 3. If it was sine, I'd plug in 5 pi over 6 because that's easier. So I'm going to say R equals 3 minus 3 cosine. Now we're plugging in for the angle. 2 pi over 3. 3 minus 3 times the cosine at 2 pi over 3 is negative a half. And this becomes 3 plus 3 halves. 3 halves is 1.5. So this is 4.5. So now I can get a little bit more accurate with my graph. I'm going to plot the point that was 4.5, 2 pi over 3. Hello. I'm going to go to 2 pi over 3 and I'm going to 4.5. So on that 2 pi over 3, 1, 2, 3, 4.5 is there. And then because it has symmetry to my polar axis, I'm going to reflect that down to 4 pi over 3. So I'm going to go 1, 2, 3, 4.5. And now I have my shape a little bit more accurate. Which to me is enough information. So it doesn't have to be perfect, but just those 4 points alone are pretty good to get you an estimate of what this graph should look like. So we talked about it yesterday, but if it had, we did one that had like the convex side. A convex is going to go max or min, max on one side, flat on the other. So it looks something like that, okay? Then we said if it was, well, I'm going backwards. If it was a cardioid, which is the one we've got, it goes to 0 and back around. So this will always have a 0 point. If I do my dimpled one, it does not hit 0. It's going to come close to 0, but it does that rounded edge. And then the last kind is your inner loop, and your inner loop will come past, cross through 0, and come back around like a pretzel. So the ones that hit 0 are your inner loop and your cardioid. The other two will not. The other two will stay on the other side of your axis, okay? But you will know this if you find the max, you find the min, and you set them both equal to your equation and you find them. It will find you those points, okay? Questions on the one we just did, because we're going to add roses. Okay. Yep. Do the limit gates is probably the easiest, okay? So that's there's light at the end of the tunnel, okay? Limicons are hardest because they're so intricate, okay? The next one are called roses, and they're pretty, right? They have petals. That's why they're called roses. So the important part about a rose, one, is identifying it's a rose, and the way we identify it's a rose is that every single one of these equations will have a number multiplied next to your theta. That number could be anything 2 or bigger. So it could be 2 theta, 3 theta, 4 theta, 5, whatever it is, okay? That number is telling you that this is a rose. If it's a rose, then we go into, does it have an even number of petals or an odd number of petals? And the way we determine that is the number that's next to your theta. If the number next to your theta is odd, so if it said 3 theta, 5 theta, 7 theta, then it has that number of petals. If it says 5 theta, it has 5 petals. If it has 7 theta, it has 7 petals. If the number next to your theta is even, then you have to double the amount to get the petals. So if it said 2 theta, there is no rose with 2 petals. That's a limnoscate, okay? Then we double it. There'd be 4 petals. If it said 4 theta, there are 8 petals. Double the amount. Also, if it has an even amount, it has all types of symmetry. I missed my R. It has polar axis symmetry, it has pi over 2 symmetry, and it has pole symmetry. So if you look, this is an even one, this is an even one. It is perfectly symmetric. The top corner reflects down, the top flips down, the left flips down over the right. It has all 3 types of symmetry. Not true for odd. Odd will follow the same rules as before. If it's cosine, it's going to be symmetric to the polar axis. If it's sine, it's going to be symmetric to the pi over 2 axis. But if it's even, it has all 3. So the first thing you're going to do, figure out it's a rose, figure out the number of petals, figure out the symmetry. And the number on the front, that A value, is the length of the petals. Notice that this says this is A. So A is your petal length. Number on the front. So I'll say it's a rose. It has this number of petals. The petal length is this, and it has this kind of symmetry. Those are the first 4 things you're going to figure out. Then we're going to go through these steps. So we're going to do the symmetry. We're going to figure out the number of petals. We'll find the length of each petal. And then we're going to take our equation and we're going to set it equal to the petal length. And that's going to tell you where all the petals are. This part is where it gets confusing because we pull back in our multiple angle equations. So if I said a half equals cosine of 4 theta. Remember that these mean it happens at wherever that answer is, but I also have to alter my interval. So cosine is 1/2, positive 1/2 in 2 places. It is positive 1/2 at pi over 3. And it is 1/2 at 4 pi over 3. Nope, 5 pi over 3, sorry. Plus the interval 2n pi. And then because this is not equal to theta, this is equal to 4 theta, we have to then take that and divide by 4. So in this case, theta would be at pi over 12 plus n pi over 2 and 5 pi over 12 plus n pi over 2. So that's going to tell you where your first 2 petals are. There's a petal here, there's a petal here. But based on this equation, how many petals are there? 8. We double it when it's even. So based on this, there would be 8 petals. We just found 2. And then we would actually take pi over 12 and add this interval, making n1. So we would add pi over 2, find that angle. That's where another petal is. We're going to take 5 pi over 12, add pi over 2. That's where a 4th petal is. And then because it has symmetry to the polar axis, we would literally reflect all those petals across the x-axis to get your other 4.
Why are you writing with pi over?
So remember your multiple angle equations, like this goes back a ways, but when you have something next to that theta, it's called a multiple angle. And the answers are not just where that answer occurs. It's that answer plus 2n pi altered by whatever's next to the theta. So once you get your answer, which typically would have just been this if it said cosine of theta, now you have to take those and divide by 4. We're going to practice it again, but that's the confusing part of roses, okay? So talk about what we know. All right. So first of all, because it's got a 2 here, we know this is a shape would be a, what did we just go over, people? A rose. Holy moly. Can we try that again? There's a number multiplied by the theta. If there's a number multiplied by the theta, what kind of polar graph is it? A rose. Good job. How many petals does this rose have? 4, because it's even, right? Also, because it's even, what kind of symmetry does it have? All of them. It's got pi over 2 symmetry, which means it's symmetric to the y-axis. It's got polar symmetry, which means it's symmetric to the x-axis. And it's got pole symmetry, which means top right, bottom left, top left, bottom right. All right, then what's your rose length? Petal length. Good. Okay, now we're going to find where the petals are. So I'm going to take my equation and set it equal to 2. I'm plugging 2 in for the r. 2 equals 2 cosine 2 theta. Then I'm going to divide by 2, and I get 1 equals cosine theta, 2 theta.
Why are you plugging in 2 for the R?
Because you want to find the petals. So we're saying, where does that petal exist? I set it equal to the petal length. All right, so where is cosine 1? 0 plus 2n pi. Then I'm going to divide both sides by 2. And I get theta equals 0 plus n pi. So my first petal is at 0. At 0, I'm going to go to 2. And I'm going to draw a petal. You with me so far? Okay, I'm going to find another petal by taking this n and replacing it by 1. So I'm going to take 0 plus pi. And 0 plus pi is pi. That's my second petal. So at pi, I got another petal. How many total petals do I have to have? 4. Where am I going to put? Good. So where would I put other petals in which it would have pi over 2 symmetry, polar axis symmetry, and pole? Only can go at the top and the bottom. So I put one here, and I put one here. So it has to have all 3 types of symmetry. If you want to check it, then the other thing you could do is say, all right, if I think that I have a petal at the top, then I could literally take this equation and plug in pi over 2. And I get 2 cosine of pi. And what's the cosine at pi?
0. Oh, pi 1.
Good. So I'd get negative 2. Now that's telling you it's not at the top, right? But where is it? It's at the bottom. So instead of going towards pi over 2, I go the opposite direction, and that's that petal. What do you think would happen if I plugged in 3 pi over 2? I'm going to get negative 2. It's going to go at the top, and I'm going to get the other one. So if you use the tricks that we talk about with all these different things, it eliminates work. If you don't know it, then you're going to end up plugging in points, which is okay. It just kills you on the time. Questions on that one? So you have to know your unit circle. You have to know how to solve multiple angles. And you have to be able to classify the polar graphs. One is a lemniscate. This is an infinity symbol. It's a flower with 2 petals. Okay? It is the easiest to identify because it is the only one that has an r squared. So it has an r squared, which means the normal shortcut rules to symmetry go out the window. I can't say that it has polar axis symmetry or pi over 2, okay? The rule is technically if it's cosine, it still works, but the shortcut on the sign does not. But just assume you don't have to know the symmetry on this because I'm going to teach you what to do. It has pole symmetry, which means as soon as you find one petal, which is really just like that loop, all you have to do is reflect it the opposite direction. So one big difference is the r squared. The second big difference is that the number on the front is a squared, which means to get the length of that petal or that loop, we have to square root that number. So if it says r squared equals 9 sine 2 theta, 9 is not your length, 3 is, because that number is your length squared. So I say my petal length or the loop length or whatever you want to call that is 3. And then I literally set the equation equal to, or I plug 3 in for the r. So I'm going to plug it in here. 3 squared would equal 9 times sine 2 theta. I'd get 9 equals 9 sine 2 theta. Divide by 9. 1 equals sine 2 theta. Where is sine 1? Pi over 2. So 2 theta equals pi over 2. Really plus 2n pi. But you don't even need the multiple angle part of this because you're just going to reflect it. Then I would divide by 2. And I'd get theta equals pi over 4. So I know one of my petals or loops is at pi over 4. And then because it only goes the opposite direction, it makes an infinity shape. I would know the other one goes the opposite side. The one that's on the other side. We're going to change this. Yeah, I'm going to rewrite this though. So we get a cosine one and a different petal length. All right. So think again, they're going to get mixed in. Like on your test, you're going to get them mixed in. You're going to actually get 3 polar graphs. You're getting one limicon, 100% you're getting a limicon. You're going to get a lemniscate, a rose, or a circle, 2 of those 3. Well, you're definitely getting a rose. So you're getting a lemniscate, you're getting a limicon, a rose, and then you'll either get a lemniscate or a circle because I feel like those are about the same level difficulty. A little bit harder for a lemniscate, but about the same. All right, so tell me what you know about what I just wrote up there. R squared equals 16 cosine 2 theta. First of all, it is a lemniscate, yes. What else do you know? Good. The length of the loop or the petal length, it's not really a petal, but it's what it looks like. The length is 4. So now I'm going to take the 4. I'm going to plug it in. 4 squared equals 16 cosine 2 theta. 16 equals 16 cosine 2 theta. Every single time I'm going to do these same steps. It's going to divide by the number there. I get 1 equals cosine 2 theta. Where is cosine 1? 0. So 2 theta equals 0. Again, technically plus 2n pi, but I don't need to find that because I'm just going to finish my shape. I'm going to divide by 2, and I get theta equals 0. So at 0, I've got one part of your infinity shape that's going to go to 4. It's going to look like this, which means the other half is going where? On the left. 1, 2, 3, 4. And it finishes it out. Questions? All right, take out your graphic calculators because we're going to go over how to check these. And I think it's at least one question on the homework tells you to use your graphing utility to graph. All right, so first of all, we are in polar. So if you were here last week, we switched it to polar to do the coordinate conversion on our calculators. If you weren't, or if you've reset it since then, make sure you go back and then you change it. So I'm going mode. And then next to parametric says polar. It has to be in polar. Then I go to my y equals, and in my y equals it says R1. So now it's already telling you, I know this is in polar, that's what it should equal. So I'm going to graph first a rose, and then we'll talk about the lemniscate. The rose we just graphed was, what was it? It was 2 cosine 2 theta. Hello? 2, okay, I'm not writing. So 2 cosine 2 theta. Oh, no, that was done. I'm going to type that in. Theta is the variable button. So when I push that variable button, it now knows it's in polar, so it's going to give you theta. It's the variable button. Because you put it in polar, it knows to change x to theta. So the one that we usually use for x, if you tap it, will be theta. If it's not, then you're not in polar. Okay, so now think about if I wanted to do a lemniscate. If it says r equals there, and my lemniscate is r squared, how could I type that in? What would you have to do? I'd have to square root, and when I square root, I'd have to do plus and minus. So 16, what do we do? Cosine 2 theta. So if I wanted to type this in, I'd square root 1 plus 1 minus. So under 1r, I'm going to get positive square root of 16 cosine 2 theta. And on the other r, I'm going to get negative square root of 16 cosine 2 theta. And then it will give you both sides of your lemniscate. So it would look like square root 16 cosine 2 theta negative square root 16 cosine 2 theta. And you'll see it just continue to build and build and build and build because it never ends. It just keeps going. So you see it change colors a little bit. It'll eventually stop. But so you don't, on the homework, it's going to ask you to literally use a graphing utility to graph one of your polar graphs. Take a screenshot of it, add it to your homework, okay? And on your test, you need to know what we did last week, which is the conversion of the points. Like there are some questions you're going to get on your test. You get a calculator portion and a non-calculator portion. And the calculator portion is the conversion from polar to rectangular and rectangular to polar. Yeah, I mean, it's more than one question on it. Two questions on it, but that's it. Questions on anything we talked about 9-6? Okay.